Okay, the primary objective of this lesson here is going to be just to run through the different values that we have in the equations for resistance. So starting here, we're just going to run through all this information and kind of just lay out the definitions. So flow is can represented by this V with a dot over it, or the Q. Q is going to be the one we predominantly use here. So flow is units of volume per unit of time. And a lot of things, it's cubic meters per second. That does not work very well in the human body, so we go with liters per minute as our flow metric. Pressure, so millimeters of mercury of pressure of blood that is applied on the vessel wall. Delta pressure, or change in pressure, is the pressure difference separated by the distance along which flow occurs. So in the body, it's going to be from arterial to venous. So the aorta, it's going to be the average pressure that we can generate from here to the venous across the entire system, right? So if we're wanting to get from here to here, that is essentially aorta to SVC, IVC, right atrium. Resistance is the resistance of the tube through which flow occurs. Compliance, highly compliant, it's going to be real stretchy. Poorly compliant, it's going to be stiff. Volume, length, radius. This is the internal dimension radius. Mu, I believe, is fluid viscosity here. Ohm, unit of electrical resistance, which is measured in this, which I'm not the guy to be explaining that. What I can explain, though, is in the sort of hemodynamic equivalent is a wood unit. The S applies that it's sort of indexed to the body surface area in meters squared. So a wood unit is millimeters of mercury per liter per minute. So the pressure can change based on flow. Moving on into Ohm's law. So voltage equals current times resistance. And so if you think about voltage, it's the potential differential. Current is flow. So what is the hydraulic equivalent that we're discussing? It's this pressure difference, right? Is flow times resistance. And so we have different ways of kind of getting through that. But if we rearrange it for resistance, it's a change in pressure over flow. And the change in pressure, as we've discussed, is arterial minus venous over flow. And again, just to hit some definitions, stroke volume, heart rate. Stroke volume is the volume of blood that is ejected by the left ventricle or right ventricle in a single heartbeat. And heart rate is in beats per minute. How many times does the heart beat per minute? So Poiseuille-Hagen, this is my phonetic note here. The relationship is the relationship of pressure and flow of a Newtonian fluid flowing through a straight round glass tube. Yeah, right. That does not apply to the organic nature of the human body, but we want to understand the significance of the different components. And so resistance is 8 times length times viscosity, so how long are all the vessels, over pi times radius to the fourth power, and the internal radius, right? So if you look at this, vascular resistance is directly related to viscosity here and length here, and inversely related to its cross-sectional area there. Last thing to cover here in our different formulas, and we're not going to really use this, but it's more for understanding the concept and the relationships. Change in pressure is related to change in volume over compliance. So something that's very highly compliant, you're going to not see much of a change in pressure as you change the volume. For example, in this graph, veins, versus something that's poorly compliant, it's very stiff, you change the volume or the pressure and you're going to see an equivalent change. And so if you recall in our previous lecture about how arteries have the smooth muscles, that you can see how as intravascular pressure goes up as in response to volume. So as I'm giving fluid, you can see how the stiffer, higher compliant arteries or less compliant arteries to veins will represent a greater increase in pressure. That's it for this lesson. All right, concepts are where this all comes together. So we're going to start with the resistance equation here, which is a change in pressure over flow, and in the body we're talking about arterial to venous. If we rewrite the equation, so it's pulmonary arterial pressure equals flow times resistance plus pulmonary venous pressure, what this demonstrates is that arterial pressure may increase due to increases in flow or resistance, which is a key concept. So if we talk about Poiseuille's Hagen relationship, and we're going to discuss length, viscosity, and radius, tackling radius first, we would think that if we just decrease the radius in half, that's going to be, have a half impact. Well, that's not the case because it's radius to the fourth power. And so the impact of that is because the body is designed through the central neural system to have dramatic control over flow, it's a very powerful method to impact flow and resistance. And for example, if I'm going to increase radius to or increase resistance to a region, that's most likely going to decrease flow, and we see that without much of a significant change in pulmonary arterial pressure because the body's designed to remain in homeostasis as much as it can be. Now, length. What is length of the vascular system? Well, one way to think about it is obesity. This is not an accurate representation. It's more for the concept, right? 1 kilogram of fat is going to result in 1,000 kilometers of capillary vessels to maintain all of that the cell viability. And so, without a doubt, we know that obesity is tied to high blood pressure, and this equation can show us how we can get there. Viscosity, increased hemoglobin in the blood relatively, that's polycythemia. Sickle cell, sort of deformed hemoglobin cells, so it can't get through as easily. Dehydration, which can result in a sort of a relative polycythemia, are all can impact viscosity. Cardiac output, right, is stroke volume times heart rate. Well, the amount of blood that an average human man, we're going to say, is about 70 milliliters ejected from the left ventricle, with a heart rate of 70 equals about 4.9 liters per minute. So when you hear about cardiac output, you're going to hear 5 liters per minute as an average. So now let's discuss systemic vascular resistance versus pulmonary vascular resistance. The reason why these are two different is because we have the systemic side and the pulmonary component, the right ventricle feeding the pulmonary system. And so aorta to vena cava, that's going to be out the aorta to the vena cava average. And again, we're going to go back to our mean arterial pressure equation to get these numbers. So if I've got 120/80 as my blood pressure, that's where I'm getting down to this 93.3 minus 4 to get, because that is the venous side, to get me down to 17.5 millimeters of mercury per liter per minute Wood units. Pulmonary vascular resistance, however, is going to be related to the pulmonary arterial pressure minus the pulmonary venous, which I can get from the left atrium. And you can see how here the pulmonary vascular resistance is much lower. So, if you think about all of these different equations, if I have a blood pressure of 150/90, I can get to what my mean arterial pressure is, and that's going to take me to resistance unit of Wood unit of 21. If I have a blood pressure of 130/80, I'm going to get all the way down to 18.6. If I've got 120/90, for example, as my blood pressure here, I'm going to get to 19.2. And so if you think about how we're using these different numbers, you're going to see how we get to the different resistance units. Here's an actual sort of cath diagram of a patient with a coarctation. But we are using this information in our clinic and in our how we're treating these patients. And we'll go into this at a later date. Great, thanks.